So what's going on since we didn't have class last time is that the homework for this week is going to be due on Thursday instead of today. So
this Thursday?
yeah, this Thursday.
Does that apply to math proofs as well?
Yeah, that applies to math proofs as well. And we're going to spend today doing what we would have done on Thursday, which is like just looking at more examples of normal subgroups and quotient groups. And then there'll be a very, very short amount of videos to watch for Thursday. And then more to watch for Tuesday, but they're going to be all based on the same thing, homomorphisms and the isomorphism theorems. And then that's enough information for 3 days of class anyway. So we'll do Thursday, next Tuesday, and the next Thursday on these homomorphisms / the isomorphism theorems. A little bit to prepare for Thursday, just a little bit, and then more for Tuesday. And then we'll be doing like examples, homework exercises, and classes those 3 days. So, okay, is that clear where we are? Okay, cool. Okay. So let's maybe recall definition of a normal subgroup real quick, and then look at some definition or some examples. So let's recall that N is a normal subgroup of G. So I'm using like the shorthand notation here. If we've got a couple of different ways to write this. One is that every coset is left and right coset at the same time. So we could write that as for all G in G, Gn is equal to Ng. So that's a left coset with coset representative little g is the same thing as the right coset with coset representative little g. But now notice this is a set description of normality, right? Because these are sets. Like cosets partition a group. They're subsets of the group. They're not subgroups of the group, but they're subsets of the group. But an equivalent element-wise description would be like this. G little n equals n prime little g for, yeah, like that. Where this is like for all little n, there exists a n prime. So in other words, you can commute G past an element from n, and you end up with another element from n, not necessarily the same one, but another element from n. Okay. And so there's this other method of noticing that you've got a normal subgroup, and that goes like this. So for all G n G, G n G inverse is equal to n. And actually you can have just a subset thing here. It doesn't have to be total equality. It can just be a subset because the subset actually implies the equality. So this is called the conjugate subgroup. So anytime you've got a subgroup, you can form something called the conjugate subgroup by doing this. So if you form the conjugate subgroup and you get the same subgroup, then it's a normal subgroup. And now let's like write this in element-wise notation, because this is set-wise notation. So this would be for all little n and n, G little n, G inverse is an element from n. And then here are some facts. If H is a subgroup of G, not necessarily normal, with the index of H in G is equal to 2, then H is normal in G. So we used this a bunch last time, right? Index 2 equals normal. And that doesn't equal normal. Index 2 implies normal. Because obviously normal doesn't imply index 2. Okay. And then maybe another one, which is actually a really important fact for like classifying groups and the so-called CELO theorems, which is like essentially the first few weeks of an Algebra 2 type class. Has to do with this: if the size of G is finite, so it's a finite group, so I'm just going to write it like that. The order of G is less than infinity. And H is a subgroup of G, is the only one of a certain order, then it is normal. Let's actually prove this second fact real quick, just kind of for funsies. Maybe I'll like make this a sun. Okay, so let's make a proof of this. So we'll clean up the claim a little bit. So let's make our claim. Let's suppose that the size of G equals N and H is a subgroup of G such that the size of H is M. And then furthermore, H is the only subgroup of order M. So maybe also H is the only M element subgroup. So that's like our setup. And then what we want to do is prove that then H is normal in G. Okay, so how can we do this? Well, we can do this by proving that GHG inverse is going to be a subgroup. So that's what we'll do. So we show for all G and G, GHG inverse is a subgroup of G. And how can we do that? We can do that with the subgroup test. So use subgroup test. Remember, the subgroup test is just a one item check to check that something's a subgroup. So let's suppose X and Y are in G inverse HG. And then by the subgroup test, we want to show that XY inverse is in that set. So let's do that. Well, this tells us that X equals little g. Sorry, I got my inverse on the wrong side. Doesn't really matter. You can equivalently define it the other way. Okay, so let's set X equal to G inverse for A and H. Right, so that's what it takes to be in this conjugate thing, right? It's got to be little g times an element from H times little g inverse. And then we can do Y is equal to little g B, little g inverse for some B in H. All right. And then now let's look at X, Y inverse. And notice that XY inverse is GA, G inverse, GB, G inverse, like that. But then by the shoes and socks theorem, when you're inverting a combination of things, it reverses the order, right? Mm-hmm. So that's going to give us a GA, G inverse here. That doesn't change. And then here we're going to have G inverse that goes forward, right? So G inverse inverse is just G. And then we'll have B inverse. And then we'll have G inverse. So notice that's from flipping the order of all of these and inverting, right? But now the magic happens. This G inverse cancels with this G down to the identity, and that gives us G A B inverse G inverse, which is an element from GHG inverse. So let's reiterate what happened here. How do we know it's in GHG inverse? Because we know this guy right here is an H, right? By the fact that A and B are an H, right? And H is a subgroup. So what did we do? We started with two elements, X and Y, from this conjugate object. And then we looked at XY inverse, and that landed inside of this conjugate object. But that's exactly what we need for this to be a subgroup. Okay. So we have GHG inverse is a subgroup of G. Okay, now we're going to show that they have this, it has the same number of elements as H. So now show the size of GHG inverse is equal to the size of H. And we can actually do that. They're actually isomorphic. And that's what we'll show instead. We'll show the stronger condition. So actually, H is isomorphic to GHG inverse. And how can we prove that? Well, let's consider phi, which goes from H to GHG inverse, which takes an element from H, we'll call it A, and it sends it to GAG inverse. Like that. And then we need to check this is an isomorphism. Right, so let's look at phi AB. Well, that's going to be GAB G inverse by the definition of phi, right? And now that's going to be GA G inverse G B G inverse. Notice we just like took a inverse pair out of the identity here. You can always introduce an inverse pair anywhere you want. But now that's great because GAG inverse is phi A, GBG inverse is phi B. So that's one of the properties we need for it to be an isomorphism. And then next, we need it to be both injective and surjective. So let's show injective. So let's suppose that phi of A equals phi of B. But that means that GAG inverse equals GB G inverse by the definition of our map phi. But then we can left multiply by G inverse, right multiply by G, and that immediately gives us A equals B. But that's what we needed, right? So phi is injective. Okay, but now let's check it out. So let's see what we know so far. We know that phi is injective and H is finite. Oh, wait, no, sorry, that's incorrect. Let's step back a little bit. So now we want to show that this is surjective. So that's the next thing that we need. Surjective. I got ahead of myself, I apologize. And then we'll have an isomorphism, and then we're like essentially done. So let's see, how can we show it's surjective? Well, generally that requires like some scratch work. So let's get set up first, and then we'll do some scratch work. So let's suppose that something is in the target. Let's call it X equals, sorry, X is in GHG inverse. So that's in the target space, right? Now we want to find a pre-image to that, but that's actually very easy just by the structure of the target space. So that means that X equals GA, G inverse for A and H. So that's by the definition of this GHG inverse. But I mean, that gives us our pre-image, right? So maybe we'll like just notice that phi of A equals GAG inverse, which equals X, which tells us that phi is surjective, implies bijective, but bijective means this. So the size of H equals the size of GHG inverse. So let's see what we've got. We've got another subgroup that is the same size as H, right? We showed it was a subgroup over there. We showed it's the same size as H right here. Another subgroup, the same size as H. But H is the only subgroup of a certain size. That means it has to be H, right? We're assuming that. This is a very special case. We're assuming that H is the only one of that size. By uniqueness of H, and that's a big assumption, but sometimes there's like some numerical tricks where you can prove that or whatever. By the uniqueness of H, that tells us that H equals GH G inverse. So we did it. Was it? I mean, but we checked all the details, right?
Yeah.
You know? And so that's just kind of the situation when you like go into all of the details. Okay. So let's look at a concrete example now, and then maybe we'll take turns giving you guys some opportunity to work on the problems. Let's look at this. Z cross Z mod the cyclic group generated by 2, 4. So let's see what that is. So what do we mean by this? Well, Z cross Z is a group made up of all ordered pairs M and N, where M and N are in Z. And then addition is the operation. So addition is our operation. So if you take like Mn plus M prime N prime, you get M plus M prime N plus N prime, like that. So it's just component-wise addition. Now let's try to get a handle on this subgroup real quick. So this cyclic subgroup generated by 2, 4. So remember, addition is our operation here. So by cyclic subgroup, we mean repeated addition, right? So this is going to have the following elements. So the identity is going to be in there. The identity is 0, 0, right? Because it's addition Z cross Z. And then we'll have 2, 4. We'll have 4, 8. We'll have 6, 12, ... Right? That's because that's combining the generator with itself 1 time, 2 times, 3 times, and back that, and forward that way forever. Then going back this way, -2, -4, -4, -8, and back like that, right? So just to like look at when we're working with an arbitrary group, we always write arbitrary groups multiplicatively. So arbitrary group, we would look at like an element, sorry, a cyclic group would have the notation G like that. So generated by G. And then we would write this as the identity. This would be G squared, G cubed. Then this would be like G inverse squared, which is G to the -2, and so on and so forth. But in this case, it's additive. So you've got to like really like pay attention when things are additive versus multiplicative. Okay, so we've got that kind of setup. Now we need to figure out, well, first of all, we know that it's normal immediately because abelian. So if you've got an abelian group, every subgroup is a normal subgroup. So there's nothing to check there. Now we just need to get a handle on the cosets. So let's see if we can do that. Well, we've got a coset, which is the group itself, right? Let's maybe give some notation. Let's say H is equal to, right, is that. And then we'll have something like this. We'll have 1, 0 plus H. That would be one example of a coset. And so that's just going to be all of the elements here where we add 1 to all of the first entries, right? Yeah. Add 1 to all of the first entries. Then maybe, let's see. We could also have 2, 0 plus H, right? So that would be like exactly everything here, except whenever we add 2 to all of the first entries. And then likewise, we could have 0, 1 plus H, 2 plus H, and so on and so forth. So let's like look at this and see, well, what kind of group structure might we get? And I think this could be a little bit tricky. Maybe let's notice some things like this. So notice if we take 2, 0 plus 0, 4, or actually, let's write them as cosets. So 2, 0 plus H plus 0, 4 plus H. So that would be two of the cosets, right? We get 2, 4 plus H. But 2, 4 plus H is inside of H, right? But since it's inside of H, that means it's the same as the coset of H. So there, we've landed on something. We've landed on the fact that 2, 0 and 0, 4 are like inverses of each other, right? Yeah. So maybe we could write it like this. 2, 0 plus h is equal to negative 0, 4 plus h. Right? Why? Because they add to the identity. Yeah. Notice they added to the identity. This is like the identity. Since they added to the identity, they've got to be inverses of each other. Okay, cool. Well, let's see. Do we have anything else similar to that? So it looks to me like from this guess, that we can make some sort of simplification here. And what might it be? So I think it's something like this. I think it's something like this maybe. So notice that here, if we, let me think for just a second. Okay, so here's my guess is that you can take all of these. So all of these, so like 0, 0 plus h, 1, 0 plus h, 2, 0 plus h, 3, 0 plus h. So you've got all of those cosets. So you've got any choice that you want in the first entry. But then in the second entry, you don't have anything you want. In the second entry, you can only use the numbers between 0 and 3. And that's because when you land back at 4, you've hit something up here. So I think you've got all of these, so you've got infinitely many elements here. And then also you have 0, 1 plus h, 0, 2 plus h, and 0, 3 plus h, like that. So you've got something going on like this. Notice if you add 0, 1 plus 0, 3, you get 0, 4. But 0, 4 is going to be negative 2, 0, right? So I should point out that this is also going back in this direction. So you've got this copy of the integers here, and then you've got this copy of the integers modulo 4 here. So let's see if we can put this together into some sort of careful description. So we'll do it as a claim. That is G mod H is isomorphic to Z cross Z4. Okay, and then how does this go? Well, you would take your isomorphism phi from G mod H to Z cross Z4, and you have to figure out what an element from here is mapped to over here. So let's see if we can do that. So an element over here looks like M comma N plus H, where again, H is this cyclic group of generated by 2, 4. And then over here, this can be sent to M and then something over there. And we have to be careful because let's notice this fact right here tells us that 0, 4 is equal to -2, 0. Like that. So how could we encode that? And then let's see, likewise, 0, 8 would be equal to -4, 0. And then so on and so forth. So it's like kind of a shifted version. Of Z4. Yeah, I can't actually, let me think about this for a little bit. Maybe we'll pick up and look at this one a little bit more carefully later. I don't actually know where that is going to go at the moment. Okay, so let's maybe take a few minutes to work on a problem or two, and then we'll look at some more examples. So we're from chapter 4, right? 10. So do you guys recall that? Yeah. So there were some exercises, not a ton, but there were some, right?
Mhm.
So let's see. Let's maybe like all look at the same one. One, 2, 5, 7, 8, 13. Yeah, maybe let's look at 5. And then we'll maybe sketch the proof of it, you know, in 5 or 7 minutes or something.
You said number 5 or number 7?
5. I think we'll probably look at both, but. Start with 5.
All right, so let's go ahead and look at this number 5.
So it says that, let's say we've got G, a group. Well, this is not what it says, but this is like breaking down the information into like a symbolic setup so that we can use it. So we've got G as a group, and then we've got N1 and N2 are both normal subgroups, right? And we want to show that N1 intersect N2 is also a normal subgroup. Okay, so let's do that. So we're going to do this using this definition of normality, which says N is normal in G if and only if G and G inverse is a subset of N for all G. Yeah. Which, let's go ahead and point out that that's the same as saying for all G and G and N, G little n, G inverse is an element from N. So this is like the set-wise definition, and this is the element-wise definition. So it's good to like have a handle on both of those. Okay, so we're going to use the element-wise definition just because I think it's a little bit easier to wrap your head around doing element-wise calculations versus set-wise calculations. But you know, that might just be me. Okay, so let's suppose that little g is an element from G. It's arbitrary. And little n is an element of N1 intersect N2. I should point out that up here in pink, I'm writing the set N, but the role being played by N in our problem is the intersection, right? That's what we're trying to show is normal. Okay. And now let's notice that by the definition of intersection, this means that N is N N1 and N is N N2. So this is just like definition of intersection, right? It's an and. Okay. But now this tells us that G little n G inverse is N N1, and that's because N1 is normal in G, right? And G little n G inverse is N N2, and that's because N2 is normal in G. Those are both givens, right? Well, the normality was given. But now we can turn this and back into an intersection. So G little n G inverse is an element of N1 intersect N2. Right? By definition of intersection again. But let's see where we started and where we ended. So we started here. We've got arbitrary G and G. We've got arbitrary little n in our N1 intersect N2. And we found out that G inverse was also in N1, N2. But this statement right here, that's my little and thing. So this underline and this underline implying this underline is what is sufficient for the normality of N1 intersect N2. So we've got it. Okay, so let's look at another example, and then we'll look at 7, or take a break out and you guys look at 7 and then 7 together too. Okay, so let's first
Oh, I want to point out that we just showed this was normal in G, and anytime you're showing something as a normal subgroup, you should immediately think about the companion notion of the quotient group. Like, what is G mod G N1 intersect N2? Well, we're actually going to find that out next week. Yeah, it's the second isomorphism theorem or something. So we'll see that next week. Okay, so now let's show that the cyclic group generated by R is normal in Dn. So Dn, that's the dihedral group with n elements. Sorry, with of an n gone. So this is one of those where you can use one of our facts. So let's notice that Dn, how many elements does Dn have? There are n reflections and n rotations. So there are 2n elements. Yeah. So there are 2n elements, symmetries of an n-gon. So think about symmetries of a 3-gon or a triangle. There are 3 rotations and 3 reflections, right? Yeah. Anytime you see like an arbitrary thing, just think about the simplest case to get the like creativity going, and then generalize it.
Yeah.
So we've got 2n elements here. And then remember, R is the subgroup of just the rotations. So how many only rotations are there? What was your answer to the first question first?
Oh,
N, yeah. N rotations. That's because Dn is made up of n reflections and n rotations. I mean, think about the triangle. You've got 3 rotations, right? You've got the identity. You've got 120 and 240 degrees, right? Okay, sick. But notice that this tells us that the index of Dn and R is 2n over n, which is 2, right? But now, by really, really important fact, index 2 means normal, right? Yeah. So index 2 implies normal. So that means we've got R is a normal subgroup of Dn. And furthermore, if you've got a normal subgroup, that means that you can do the next thing, which is look at the cyclic subgroup. And so let's look at Dn mod R. And by the index, we know exactly how many elements there are in this. So this is a group with 2 elements, right? 2, because there's like, the index is 2. That means there's 2 cosets. And what are the 2 elements? Well, there is, I'm going to write it like this, ER. So there's the identity coset. Generally, you don't write the E there, but just to make it look like a group, we will. And then there is, how do you find another one? You pick any element not in that cyclic group generated by R, and then you make a coset out of that. So S is not in there, right? So we've got SR. Yeah, and then we can make a table here. So we've got ER, SR, ER, SR. So E combined with itself is the identity. Well, E combined with S, that's obviously the identity. Or sorry, that's obviously S because E is the identity. And then S combined with itself is S squared. But S squared is the identity, right? Because it's a reflection. Reflection's always square to the identity. So this is the identity. So now that looks a lot like Z2, right? But there's only one group of order 2 and it's Z2. So not super surprising. So what do we have in the end? We have Dn mod R is isomorphic to Z2. And we can take that by taking the identity. to 0, and this single reflection goes to 1. And then you can see that, well, the charts overlap, right? Yeah, so that's going to clearly be that. Okay, so good. Now let's look at, so think about this example and look at number 7. They're related.
So essentially the same.
Well, number 7 is written in a way so that it sounds more general, right?
Yeah.
Yeah. But so like read number 7 and think about this example as, all right, I'll give you a few minutes. All right, let's look at this problem. So the question says, H is normal in G. H and GH are abelian, then G is abelian. So prove or disprove. Disprove.
Oh.
Our example gives us, our example that we just looked at gives us a counterexample.
Oh, yeah.
So 7. Not true, then counterexample. Well, there are tons actually, but I think DN is a really good one. Let's and since we did that more in generally for DN and for counterexamples, it's often quite nice just to do like the simplest version. Let's take D3. So notice D3 is not abelian. Right, we know that it's not abelian. For example, RS equals SR cubed, right? Which is not equal to SR. So not abelian, but then the cyclic subgroup generated by R is normal in D3, is abelian. What I mean, this cyclic subgroup is abelian. Well, all cyclic groups are abelian, right? So that's fine. And D3 mod this is isomorphic to Z2 is also abelian. And we know that that's abelian because, again, it's a group of order 2, but groups of order 2 are always abelian. They're always cyclic. They're only Z2. So we've got subgroup abelian, quotient group abelian, but the parent group is not abelian. Here's another example. Let's take Q8, so quaternions. So remember that's plus minus 1, plus minus I, plus minus J, plus minus K. All right, that's a group of order 8. And then there's actually like a bunch of cool examples here. Let's recall that how the multiplication goes. I'll just draw this picture, which we've drawn before. So remember, there's this loop. So I times J is equal to K, J times K is equal to I, K times I is equal to J. But then if you go the reverse the arrows, you get the minus sign, right? And then also I squared is the same thing as J squared is the same thing as K squared is the same thing as -1. So this is not abelian. And that's because IJ is equal to K, but that's not equal to -K, which is equal to JI. So again, not abelian. Okay, and now let's look at the cyclic subgroup generated by I, maybe. So the cyclic subgroup generated by I, well, that's normal in Q8. So how do we know it's normal? Well, normal because index 2. Again, this has 4 elements. 4 elements. It's cyclic, which implies abelian. And it's index 2, which implies normal. Right? 4 elements, 8 elements, 8 divided by 4 is 2. But that tells us again that Q8 mod I is equal to Z2, which is also abelian. So we've got quotient group abelian, subgroup abelian, parent group non-abelian. Okay, there's actually another example that you can make out of this. There's a 2-element normal subgroup, which is plus minus 1. So this is like generated by -1. That's a normal subgroup of Q8. I'll let you guys check that it's kind of obviously normal because this is the center. Like these commute with everything in there, right? Plus and -1 commute with everything in the group. So if it commutes with everything, then it's in the center, then it's normal. Okay, so this is abelian. Again, because it's cyclic. And then Q8 mod -1 is a group with 4 elements. None have order 4. So you can check that none of them have order 4, just like by making a Cayley table. So the 4 elements will be the coset with the identity, the coset with I, J, and K. I think we calculated this one in class already, but there are only 2 groups of order 4. There's the cyclic group of order 4, but this can't be that because none of the elements have order 4. So that means that this is isomorphic to Z2 cross Z2, which again, you can see just by like, I think we did this example last time even. Yeah, I think we did. But this is also abelian. Right? So we've got quotient group is abelian, subgroup is abelian, but the parent group is also not abelian. Yeah. So suffice it to say, there are tons of examples. I mean, all of these examples just started with parent groups of order 6 and 8, right? Which is the smallest order for a non-abelian group. So you can imagine that you would get exotic examples higher up, right? Okay. So is this clear?
Yeah.
Now, let's see. I think we've got time for you guys to look at one more and then us to look at it together. Oh, 7, 8, 13. So 8 or 13.
13.
No, that we got too much time for. There's not enough time for that. I know that's a nice and juicy one, right? Yeah, but we don't have time to look at that one. Let's look at 8. We can look at 8. All right, let's look at this last one. Wow, not the last one, but the last. Yeah, the last one for today. Just maybe before we do, for people that are maybe on the Zoom that weren't here before, I want to reiterate that there'll be a few small videos to watch before next time. And the next bit of information we're going to look at is regarding homomorphisms and the isomorphism theorems. And we're going to let that take Thursday, next Tuesday, and the next Tuesday. Just a couple of videos to prepare with for Thursday and then more for Tuesday. And then next Tuesday will be kind of the normal week. This homework is not due tonight, but it's due on Thursday. Just we moved it because of not having class on last time. Okay, sick. So this thing says if something is cyclic, then something else is cyclic, right? So if G is cyclic, then G mod H is also cyclic. So show if G is cyclic, then so is G mod H. Okay, so here is a little bit of a fact. And that is that if G is cyclic, then H is also cyclic. So that's maybe what we'll do as our first claim. So H is a subgroup of G must be cyclic. In other words, every subgroup of a cyclic group is cyclic. Okay. Good. So let's prove this. So let's say that G is a cyclic group, but that means it needs to have a generator. So let's just call the generator little g, just for the sake of argument. So that means that G is of the form E, G, G squared, G inverse, back like that, right? So it could be infinite. We don't know. A priori, we don't know if it's infinite or not. If it's finite, then, you know, it makes a cycle, which is why it's called cyclic. Okay. Now, let's take n in the natural numbers to be the smallest such that G to the n is NH. Well, check it out. H is a subgroup of G, right? That means it is made only of elements from G. But then since it's made only from elements from G and everything in G is just a power of little g, that means everything in H is also a power of little g, right? So what we're doing is taking the smallest power of little g that is in H, but not the smallest integral power, the smallest natural number power. So maybe it's G squared or G cubed or G to the fifth or something, right? And now we're going to make the following claim, which is we show that H is in fact equal to the cyclic subgroup generated by n, little g to the n. Okay, so we're going to do this by double set inclusion. So let's first notice that the cyclic subgroup generated by little g to the n is obviously a subset of H, right? So that's because Gn is in H and then H is a subgroup. So that means that everything generated by G to the n is in H. So what we want to show is that H is a subset of this little g to the n. Okay, so let's do that. So let's suppose that G to the M is in H. Okay, well, we know that it has to be of the form G to some power, right? We know it has to be of the form G to some power because H is a subgroup of this cyclic group. Now, use the division algorithm with M and N to write M equals N times D plus R, where R is between 0 and N, like that. Okay. So from here, what you can do is take G to the M and write it as G to the N D plus R. That's how we wrote that thing right there. But that's going to be equal to G to the N to the D power times G to the R, right? But let's notice that that means G to the R equals G to the M times G to the N to the minus D, just by moving that over, right? But now check it out. G to the M and G to the N are both inside of H, right? So that means G to the R is also inside of H. It's because both of these are inside of H. So let's see what we've got. We've got a power of G, which is inside of H, and that power is between 0 and N, right? But N is supposed to be the smallest one, the smallest natural number. Well, every number between 0 and N is a natural number except for 0, right? So R is equal to 0, right? So otherwise, N is not minimal, right? Because we've got G to some power smaller than N is inside of H, but that's not allowed. Okay, so R is equal to 0, but notice that that means that M equals N times D, or G to the M is equal to G to the N to the D power, but that's an element of the cyclic group generated by G to the N, right? It's the Dth power of G to the N. So that means we finished this proof that H has to be cyclic, and then let's just sketch out how to prove that G mod H is cyclic. Now you can really just look at G mod H, which notice that's equal to the cyclic group generated by G mod the cyclic group generated by G to the N. Oh, yeah, that's right. So here's a more of a hint. This is cyclic with generator G times G to the N. But there's a little bit more to check there, but not a ton, but a little bit more. Okay, good. So I think we're good. Everyone have an idea what to do for next time?
Yeah.
Okay.
Can I see the first square real quick?
Yes. Right there. Is that good?
Yes, thank you.
Great. Oh, her voice came through here. Why am I wearing my headphones if her voice came through here? I don't need these. This is only to hear them. My settings must be wonky.
Or to your phone instead.
No, I don't think it's that.
Or they're dead.
Because I just had something on while like you guys were working on this quietly. Yeah. Pretty big fever. 102. Yeah, I'm a little baby about this kind of stuff, though. Not to like speak ill of babies, but I seem to be particularly affected by just small illnesses. Kayla, are you all set, or do you need more?
I'm good. Are
Okay,
we
great.
done for today?
What?
Are we done for today?
Yeah, we're done for today.
I don't know, once I get a headache, I'm down for the count. Oh, I'm just like inactive.
I just power through the class.
I can't do it. I'll still stop.
Well, I mean, you won't feel bad until like much later.
I'll still